Welcome back to this course on abstract algebra. Today we're going to start in earnest with abstract algebra. We are in fact going to define what is a group. So let's get started. Our groups are going to be modeled after our prototypes that we constructed in previous lectures. Well, the integers under addition, that is a group. Or, for example, we also saw the integers modulo a fixed number n under addition. That is also going to be what we call a group. Notice that, of course, the integers have more than one operation. They also have multiplication. But a group is only going to be a set with respect to one operation, such as these two. So actually, before we get started with group, let me define what this operation is. So that is what we call a binary operation. So a binary operation on a set G is a map, a function from G cross G to G. I'm going to call these operations by a star. So it's just a function. By the very properties of the very definition of function, what that means is that, i.e., for each A and B elements of G, there is a unique element C also in G, such that A star B is C. So that's what we call a binary operation. And as I said, for example, for the integers, addition is a binary operation, and multiplication in the integers is also a binary operation. But addition in z modulo nz is also a binary operation, and so is multiplication. Okay, so what is a group? Then a group is going to be a set with a binary operation, with a chosen binary operation. So here's the definition. A group is a pair of a set and a binary operation. So of a set G and a binary operation star from G cross G to G, such that, by the way, sometimes we say, instead of there exists a binary operation, we just say that the first property is that G is closed, is the word that we use under the operation star, i.e., that for any, as I said before, for any A and B in G, A star B is another element of G. Okay, but I'm just going to say that G and star, that star is a binary operation on G, that satisfies the following properties. One, we're going to assume that star is associative, and that A star B star C is the same as A star B star C for all A, B, and C in G. Why do we need this? We need this because binary operations only tell me how to operate on two elements at a time. So it needs to tell me how to operate on three elements at a time. And if I'm going to operate on three elements, it should be the same as if I operate on the last two and then use the third one, or I operate on the first two and then use the third one. So that's why we need associativity, and it's a a rule that is many times so it's so natural to us that we don't realize we're using associativity, but it is very important. We'll emphasize a couple times where associativity is very much necessary. Second, there is an identity element or a neutral element, E in G with respect to a star, i.e., for every A in G, we have that A star E is the same as E star A is A. So it doesn't do anything when I operate with these element E. And G3, we have inverses. For every A in G, there exists another element that I'm going to call A inverse, and that is just a name for this element. It's just some other element in G such that A star A inverse is the same as A inverse star A is the identity element where E is as in G2. Okay, and that is it. This is the definition of group. This is a group. And now we are going to also define a abelian group. So let G star be a group. So star is a binary operation. It satisfies G1 through G3. And then if in addition G satisfies G4, which is that for all A and B in G, we have that A star B is the same as B star A, then we say that G is an abelian or commutative group. Okay, great. So we have seen already examples of groups. So let me just indicate again that our prototype of group is the addition, the integers under addition. But we also had, for example, the reals under addition or the rational numbers under addition. These are groups, and one can show that they satisfy all of G1 through G4. So these are abelian groups. Oops. These are abelian groups. Similarly, if n is fixed, z modulo nz under addition is also an abelian group. But this one is quite different because this is finite, while these, the reals, the integers, the rational numbers, these are all infinite. So that is our first example of what we call a finite group. So let me define that. Let G plus G star be a group. Then if G itself is a finite set, then we say G is a finite group. Otherwise, if G is infinite, we say G is an infinite group. If G is finite, the order of the group, the size of the group, if you want, hashtag G, is called the order of the group. And it's equals the number of elements in G, and the number of distinct elements, if you will. So, for example, Z modulo NZ is finite of order n. Is a finite group of order n. Okay. So, what are other examples of groups? We've seen a bunch of abelian groups. So let me show you some non-abelian groups. Remember that we had discussed in a previous example, you can do the symmetries of an equilateral triangle. So if I have an equilateral triangle ABC, the symmetries are those operations that leave the shape of the triangle untouched. It can like change the position of the vertices, but it just leaves the shape of the triangle untouched, such as a vertical reflection or some other reflections or some rotation by 120 degrees, etc. Under composition, we saw that actually this is an abelian group. This is a group that is non-abelian. So this is a group, but is non-abelian. And you can see we showed previously a composition of two different symmetries that are not leaving the triangle. Those symmetries do not commute. Let me give you another example. So if I take M matrices that are 2 by 2 with real coefficients under matrix multiplication, this is not a group. Because, for example, this is not a group because it fails to have, let's see, if we look at the properties of group, it fails to have inverses for every matrix. So, for example, this cannot be a group. It fails G3 because, well, for instance, a matrix such as this one does not have an inverse such that an inverse times this one would have to give me the identity matrix, and there is no such thing. However, I can fix that and talk about GL2 over with real coefficients under multiplication. Remember, these are matrices A, B, C, D with AD minus BC non-zero. All of those have inverses, and the matrix multiplication is associative. The identity matrix is the neutral element with respect to multiplication, and we have inverses, so this satisfies, it's a group. This is a group, but it is non-abelian. It is not a commutative group, because, for example, I can I showed this example before, so let me just write it here again, that the product of matrices 1, 1, 0, 1 times 0, 1, 1, 0 is 1, 1, 1, 0, but the product of 0, 1, 1, 0 and 1, 1, 0, 1 is 0, 1, 1, 1, and these are not the same. Therefore, matrix multiplication does not commute. Okay, let me just try to make this. So these are not the same matrices, so matrix multiplication does not commute. For a group to be non-abelian, it's enough that it is enough that two elements do not commute. That makes the entire group non-abelian. If I want to show that a group is abelian, then I have to show that every pair of matrices commutes. Okay, so we're going to now sort of, it's the step that I mentioned, like how to do abstract algebra. We abstract, then we define something, and then we profit by proving theorems that apply to all groups. So let's prove some theorems. So here's my first theorem that I'm going to prove for all groups, is that the neutral element is actually unique. So let G star be a group, and let E be its neutral element. Then E is unique. In principle, you could imagine that a group could have more than one neutral element, more than one element that works as a zero under that multiplication or under that addition. But that is not the case. Every group has only one element. In the way we are going to prove this is by supposing there are two such elements. So suppose E and E prime are neutral elements. So these means that these are elements in G that satisfy the property in the axiom, so that for every G in G, we have that, well, E is neutral, so E star G is the same as G star E is G, and also E prime is neutral, so E prime star G is the same as G star E prime, it's G. So this happens for every element G. Then what I want to conclude is that E and E prime are actually the same neutral element to prove that there can only be one. So let me start with E and then use these equations in my favor. And what I'm going to do is I'm going to first just I'm going to use these equations, but I'm going to apply for this G, I'm going to put E prime, and for this G here, I'm going to put E, because this tells me that, well, E is equal to E star E prime. Here I am using, here I'm going to put E, and then if this is E, this reads that E star E prime is E, and therefore is this property right here. So what I've used here is that E prime is a neutral element. And now I can use the fact that E is a neutral element. If I put E prime here, then this tells me that E times E prime is E prime. So this is E prime because E is neutral. And therefore, what we've just shown is that E and E prime are the same. So all neutral elements are identical. Are identical. And that concludes the proof that I wanted. Okay, let me do one more proof about properties, which is something similar, which is the following theorem. Let G star be a group. And let G be arbitrary, some element of G. Then the inverse of G with respect to star, so the one that appears, I think, in property G3, is unique. Again, you could imagine that maybe there is some group out there where there is some element G with two inverses, but it turns out that that is not possible in a group. Every inverse is unique. So let me do like I did before. So suppose that G1 and G2 are inverses of G with respect to the binary operation star. Then, by definition, G1 star G is the same as G star G1 is equal to, well, G. Oh, no, the identity, right? That's the property of that is the property of an inverse. And similarly, G2 also works as the identity. So G2 times G is the same as G star G2 is the identity. Great. So now I want to show that G1 is equal to G2. So then what is G1? Here's a common trick to be able to now bring G2. What I'm going to do, which is something we use all the time, is that I'm going to either we have an equation and we add 0 or we multiply by a 1, and then we do some operation for a 0 for 1 to bring other things into the same equation. So G1 is the same as G1 star E, where here I've used the fact that E is neutral. And E, now I have some expressions for E right here. So I want to bring G2 into the picture. So I'm going to use one of these. So I'm going to use that E is equal to G times G star 2. So E is, I'm just going to substitute here by G star G2. Okay, and I just substituted here, but I mean, really I'm substituting E by the property, the fact that G2 is an inverse of G. And now I'm going to use associativity to write this in another way. This one is now associative property. And as you see, if there was no associativity, this would not be true. And that means associativity is very important in this particular step. G1 star G is equal to E. So this is E is star G2. Here I've used the fact that G1 is an inverse. And now E star times G2 is G2 because E is neutral. And that's it. Now you see that we have that G1 equals G2 like I wanted. That's G1 equals G2. And as before, that means that there is only one possibility for an inverse. Great. Something else that I wanted to show you is that if we have a finite group, then we have what we call Cayley tables, Um, so what is a Cayley table for a finite group? It's a table where we represent all the possible operations on that group. So let me just show you by example. I'm going to do it for, first of all, for Z mod 4 under addition. So what we do is, because we have a finite group, I can actually write all the possible operations. The elements in Z modulo 4 are 0, 1, 2, and 3, considered as modulo 4 classes. So the possibilities are 0, 1, 2, and 3, and 0, 1, 2, and 3. And I can add these numbers together. 0 times anything will give me the same number back. And now in here, I would write 1 plus 1, that's 2. 1 plus 2 is 3. But 1 plus 3 is 4, and 4 reduces to 0 modulo 4, so I get 0. 2 plus 0 is 2. 2 plus 1 is 3. 2 plus 2 is 4, which is 0. 2 plus 3 is 5, and 5 is 1 modulo 4. 3 plus 0 is 3. 3 plus 1 is 4. 3 plus 2 is 5. 3 plus 3 is 6, which is 2. And this is the entire possibilities, all the possibilities for addition in Z modulo 4. So it represents the entire group. This represents what can happen under this binary operation for every pair of elements in the group. Let me give you another one. This time I'm going to do the symmetries of a rectangle under composition. And just remember, there are 4 under composition. There is the identity. There is what I'm going to call phi 1, which is a 180-degree rotation. Phi 2 was a vertical reflection. And phi 3 is a horizontal reflection. And I'm going to write identity, phi 1, phi 2, and phi 3. If I compose with identity, I get the same symmetry back. And now I start composing. Phi 1 and phi 1, if I do a 180-degree rotation and then 180-degree rotation, what I get is the identity. Notice that if I do the vertical reflection and the vertical reflection, compose those, then I'm going to get the identity. So there is an identity here, and a horizontal reflection followed by a horizontal reflection also gives me the identity. Those are the fact that there are these in the diagonals come from the fact that every one of those, the inverse is itself, or that when I do it twice, when I compose an element with itself, I get the identity. Okay, so what else can I do here? Phi 1 composed with phi 2, I get phi 3. And the same, actually, if I do phi 2 composed with phi 1, I also get phi 3. And get phi 2 here, phi 1, phi 2, and phi 1. And that is the entire table of what happens under composition for the symmetries of this rectangle. Let me do one third example of a Cayley table, which is that I'm going to do Z modulo 2 cross Z modulo 2 under addition. What are these? These are pairs of numbers A modulo 2, comma B modulo 2 under addition, where the addition is component-wise. Okay, so if I want to add, say, 0, 1 and 1, 1, then I add component by component. So this would be 0 and 1, I get 1. And 1 plus 1, I get 2, but this is congruence is modulo 2. Each coordinate is modulo 2, so 1 plus 1 is 2, which is 0 when I reduce modulo 2. Okay, for example, I get that. Okay, so now I'm going to draw the Cayley table for this group. So what are the elements? This is a direct product of two sets of order 2. So the direct product will have 2 times 2, 4 elements. The elements are 0, 0, 1, 0, 0, 1, and 1, 1. And similarly, I'm going to write them all here. 0, 1, and 1, 1, and then start doing addition. If I add 0, 0 to anything, I get that same element back. So I get these ones. Now, what happens if I add 1, 0, and 1, 0? That will be 2, 0, which when I reduce, I get 0, 0. 1, 0 plus 0, 1, that will be 1, 1, and 1, 0 plus 1, 1 will be 2, 1, which reduces to be 0, 1. And then I can keep going like this. This will be 1, 1, 0, 0, 1, 0, and 0, 1, and 1, 0, and 0, 0. And that's the Cayley table for this group. And now, what I want to show you, I want to end this video with, is that I can now compare groups and see if they have the same Cayley table. So the elements are named different things, but it could be that if I just rename my elements in a different way or reorder my elements, that I get exactly the same Cayley table, and therefore it would be the same group. That is what we're going to do in the future, is trying to classify groups, finite groups, up to what we're going to say isomorphism. And by isomorphism, we mean that, well, this set with respect to this operation, the two look exactly the same, then they're going to be isomorphic. So now what you can see is that, for example, in this one, I get all identity elements in the diagonal, and it happens, the same thing happens in here, that all the elements in the diagonal are zeros. And if you, in fact, now call these elements identity phi 1, phi 2, and phi 3, then you'll see that wherever I see phi 3 here, phi 3, phi 3, phi 3, I see phi 3, phi 3, phi 3 in here too. So these two are actually exactly the same group. They just have different names for the labels of the elements, but the arithmetic in these two groups is exactly the same. So we will say that these two groups are isomorphic. However, we see that this one is different. There is no zeros along the diagonal, but in fact, there will never be. Maybe I just can reorder these numbers so there are zeros in the diagonal, but it turns out it will never be the case. Why? Well, it will never be the case because, for example, I have that 1 plus 1 is 2 modulo 4, which is not 0. So 1 is it's not its own inverse. And one property that we see in these two other groups is that each element it's its own inverse every time. Like in here, every element it's its own inverse every time. But the fact that 1 is not its own inverse means that this group cannot be isomorphic to these two. So this one is non-isomorphic to the other two. So that is one way to tell that these groups are actually, there's at least two types of groups represented in these Cayley graphs, in these Cayley diagrams, or these Cayley tables. And the last thing I want to say, which is something we will look at in the next video, is the following. Look at the rows in this table and the column in each table. You see how every number appears, but in different orders. There are just different permutations of the same numbers, and there is no repetitions. The same thing happens in every row and every column in each one of those Cayley tables. And that is a feature of groups that we will see. Actually, in the next video, we'll explain why that happens, more or less. We will come back to this topic also in a while, but I think in one of the properties I'm going to show in the next video will show this. So I'll stop here, and in the next video we'll prove some more properties of groups.